So good morning. So in the last class, we were discussing about how to measure the rate of infiltration by using the single ring infiltrometer, or it is also called as tube infiltrometer, and the double ring infiltrometer. So in the single infiltrometer, you have a single cylindrical tube of about 60 centimeter depth and 30 centimeter width. So it is driven into the ground to a depth of about 50 centimeter and 10 centimeter projects above the ground surface, and water level is maintained to a depth of about 5 centimeter above ground level. So in the double ring infiltrometer, you have two rings. One is the inner ring and the outer ring having a diameter 60 and 30 centimeters respectively, and the height of which is about 20 centimeter, and 15 centimeter is 25 centimeter. 15 centimeter is driven into the ground vertically, and it projects above 10 centimeter above the ground level, and here also water level is maintained to a depth of about 5 centimeter. And you can also see here you have a hook gauge. So here you can record the depth of water that has infiltrated. That means the amount of water that is required to bring back the water level to a particular mark, that is the standard mark. So here the advantage of this double ring infiltrometer is the advantage of a double ring infiltrometer is here whatever the water that infiltrates moves vertically downwards, whereas in the case of single infiltrometer, so there are every chance of water moving laterally when it infiltrates below the ground surface, and water moves laterally. So whereas in the case of double ring infiltrometer, you have the advantage, water will directly move downwards and you will get the correct values of infiltration. So now the double ring infiltrometer, this is the most commonly used flooding type infiltrometer. It consists of two concentric rings driven into the soil uniformly without disturbing the soil to the least depth of 15 centimeter. The diameter of rings may vary from 25 to 60 centimeter. An inner ring is driven into the ground, and the second bigger ring around that helps to control the flow of water through first ring. So water is supplied either with a constant or falling head condition, and the operator records how much water infiltrates from the inner ring into the soil over a given period of time. So now, infiltration. So now we have discussed how to estimate the rate of infiltration by using the equipments like the single ring infiltrometer and the double ring infiltrometer, or you can have a ponds or small pits, and also in that also you can measure the rate of infiltration. Now, infiltration rate. The infiltration rate is the velocity or speed at which water enters into the soil. So this mainly depends on the porosity of the soil. If the soil is porous, obviously the rate of infiltration is more, and if the soil is impervious, obviously the rate of infiltration is slow. So basically infiltration rate is the velocity or speed at which water enters into the soil, and it is usually measured by the depth. So it is expressed in terms of centimeters or millimeter of the water layer that can enter into the soil in a particular given period, in a particular given time period. So the rate at which the water enters the soil at the surface, it is denoted by F. So with respect to time. So infiltration mainly depends with respect to time. So the rate of infiltration is always expressed in terms of F. So that is in the bracket, you can see the time factor. So now cumulative infiltration, accumulated depth of water infiltrated during the given period, it is denoted by capital F. That is the total infiltration. So now, this can be calculated by using the equation. So this is the total infiltration that has taken place in a given time. So that is integral of 0 to t F, that is F dt. So F is a function of time. So infiltration is a function of time. So you can calculate the total infiltration by using this equation. Now, Infiltration equation, infiltration capacity rate curve. So now whatever the curve that you can see here, this is the rate of infiltration with respect to time, and this is called as Horton's infiltration curve. Horton infiltration curve, and the total infiltration, that is FT. FT is given by F suffix C plus F naught minus Fc into e to the power of minus KT. So this curve is nothing but the Horton infiltration curve. So in this equation, Ft is nothing but the total infiltration, that is equal to Fc plus F naught minus Fc into e to the power of minus KT. And here, Fc is nothing but the constant rate of infiltration, and F naught is nothing but the initial rate of infiltration. So in the beginning, the rate of infiltration will be obviously high, and as the time elapses, the rate of infiltration starts depleting because initially it will be very high. So that is known as the initial infiltration rate. And as the soil moisture builds up, the rate of infiltration gradually decreases and it attains a constant rate. So this constant rate of infiltration is given by the uh, letter F suffix C. So this is the infiltration equation. It is developed by a gentleman known as Horton. So hence it is called as Horton's infiltration equation, infiltration curve. So whatever the curve that you can see here, so this curve is known as the Horton's infiltration curve. So infiltration capacity rate curve as obtained from infiltrometer is essentially to observe the decaying curve or maximum to minimum. Decaying curve means it is exponentially reducing from the highest to the lowest in an exponential form. So some mathematical expressions to describe the shape of the curve is given by various investigators. So Horton's equation, so Phillips equation, Kostyakov equation, and Horton's equation. Basically, Horton's equation is generally used throughout the world in order to estimate the rate of infiltration at a particular time period in a given soil. Now, this Horton's equation, it is of the form Ft. So always infiltration is a function of time. Function of time is equal to the constant rate of infiltration, whatever the constant rate of infiltration, plus F naught minus Fc into e to the power of minus Kt. So here, Ft is infiltration capacity in millimeters or centimeters per hour. So since we will not be using this unit inches, it will be either in millimeters or centimeters per hour. And F naught is initial infiltration capacity, and Fc is minimum infiltration capacity or the constant rate of infiltration, and time is time since the start of the beginning of the rainfall. So here K is a constant depending upon the soil type and vegetal cover. So here e to the power of minus Kt is K is a constant depending on the soil type and the vegetation cover. So note Fc is direct dependent upon the hydraulic conductivity. So mainly what this means it depends on the porosity of the soil. It depends on the porosity of the soil. The hydraulic conductivity mainly depends on the porosity of the soil. Now you can see here, this is the typical Horton's infiltration curve. Here the infiltration rate in centimeters per hour is given, and it is along x-axis. Time is considered either in hours or minute. So now initially the rate of infiltration will be very high. So hence it is called as F naught is equal to infiltration rate. That is the initial rate of infiltration. As the time progresses, the rate of infiltration starts decreasing and it attains a constant rate. Now you can see here this straight line. This straight line indicates the constant rate of infiltration. That is the final constant rate of infiltration. Now you can see here below this curve. So this curve is called as infiltration curve, or it can also be called as Horton's infiltration curve. Now you can see this shaded area. So the area below this curve, above this line is called as the shaded area. It is designated by F capital F suffix C. So this is required in order to calculate the value of K. So in this equation you have F is equal to Fc plus F naught minus Fc e to the power of minus Kt. So this value of K is a constant which depends on the type of soil and also the vegetation cover. So K is given by the equation F naught minus Fc that divided by the shaded area, whatever the area below this curve. So this shaded area is referred as Fc. So once you get this value of K, so you know the constant rate of infiltration, what is the constant rate of infiltration, and what is the initial rate of infiltration, and e to the power of minus K. So here only this is unknown, so this can be found by using this equation. So finally we'll get the rate of infiltration in a particular time period in a given soil condition. Now, so classification of infiltration capacity. So now here infiltration class, that is the whether it is very low or medium high, and infiltration capacity that is less than 2.5 millimeters per hour, in between 2.5 to 25 millimeters per hour, and it is medium, it is 12.5 to 25. So here it is not 25, it is 12.5. And if you have a high rate of infiltration, it is greater than 25 millimeters per hour. Now the remarks column, if you have a highly clayey soil in a given area, the rate of infiltration will be very less. It is below 2.5 millimeters per hour. And if you have shallow soil, clayey soils low in organic matter, then the rate of infiltration will be between 2.5 to 12.5 millimeters per hour. And if you have a sandy loam or silt, the rate of infiltration will be between 12.5 to 25 millimeters per hour. And if you have a deep sand, well-drained, aggregated soil, then the rate of infiltration will be very high. So why this is required is the rate of infiltration is required in a given catchment area because of to estimate the quantity of runoff that comes out of the catchment area. In order to estimate the quantity of runoff after meeting all the losses, what is the volume of runoff that comes out of the catchment area mainly depends on the how much water has infiltrated into the ground surface. So the remaining water, after filling all the surface depletion, it comes out of the catchment area, then finally it joins the natural stream. Now we have the things like infiltration index, or it is also called as infiltration indices. So for consistency in hydrological calculations, a constant value of infiltration rate for the entire storm duration is considered or adopted. So this is basically an assumption. So we have to assume that in a given catchment area, we should assume that a constant value of infiltration rate for the entire storm during a time period. So the average infiltration rate is called as the infiltration index. So now here in this graph, this is the constant rate of infiltration. Initially, the rate of infiltration is high. As the time progresses, it attains a constant rate. So this constant rate of infiltration is usually assumed in a given catchment area in order to estimate the infiltration in a given catchment area. So this is called as the infiltration indices, or it's also called as the infiltration index. The two commonly used infiltration index or indices are the phi index, and the second one is W index. So here you have two types of the infiltration indices. So in the examination, generally you have questions on this. So what are infiltration indices? So explain the two most commonly used infiltration indices. That is, one is the phi index, the other one is the W index. So they are extremely used for the analysis of major floods when the soil is wet and the infiltration rate becomes constant. Now here, so we have the two figures here. We know what is a hydrograph. Hydrograph is nothing but a graph of rainfall intensity in centimeters per hour versus time in hours. Now here, hydrograph is basically a bar graph. You can see here, this is a bar graph. Now, if you superimpose the infiltration curve on the hydrograph, The area below this curve, refers the infiltration. This is the infiltration curve. The area below this curve refers the amount of water that has infiltrated into the soil or the ground surface, and the area, whatever the shaded area that you can see here, it is nothing but the volume of water after meeting the infiltration. So that is known as the surface runoff. So what here we have done is we have drawn the hyetograph. Hyetograph is a graph of rainfall intensity in centimeters per hour versus time. So we'll get a bar graph. We can superimpose the Horton's infiltration curve on this hyetograph, and the area above this curve refers the surface runoff, and the area below this curve refers the infiltration, whatever the water that has infiltrated into the ground surface. So by this hyetograph, we can estimate the volume of surface runoff from a given catchment area. Now, the average value of infiltration is called infiltration index. So we need to consider an average or a constant value of infiltration for a particular catchment area, so which is called as the infiltration index, or it is also called as infiltration indices. So now here we have two types of infiltration index. One is the phi index. Phi index for a catchment during a storm depends on the soil type, the vegetation cover, and the initial moisture content of the soil. So phi index is basically assuming a constant rate of infiltration, So here we have superimposed the Horton's infiltration curve. So initially the rate of infiltration is high, and as the time progresses, it starts depleting in an exponential form, and it attains a constant rate. Now, in order to calculate this phi index value, we have considered the same hyetograph, and we have divided this hyetograph into two parts. One is the surface runoff, the other one is the infiltration. So this line, whatever this line, it's called as phi index line. So basically phi index line is a line which divides the hyetograph into two parts. One is the surface runoff and the other one is the infiltration. So basically phi index is nothing but you're going to establish a constant rate of infiltration, or you are going to assume a constant rate of infiltration. Thereby, you can calculate the volume of runoff and also the amount of water that has infiltrated. So application, estimation of flood magnitude due to critical storm. So phi index helps us to estimate the quantity of flood that can be expected, or the magnitude of flood that can be expected in a given time period by a critical storm. So next is, you can see here, this is the phi index. This is defined as the rate of infiltration above which rainfall volume will be equal to runoff volume. That means the phi index line divides the hyetograph into two parts. One is the surface runoff. The second one is the rate of infiltration, or the amount of water that has infiltrated. Now, you have one more index, W index. W index is nothing but, it is also here average infiltration rate during the storm when the rainfall intensity is greater than infiltration rate. So here, in case of W index, the average rate of infiltration during the storm is considered such that the rainfall intensity should be greater than the infiltration rate. So here, in case of W index, it is given by the equation P minus R minus IA divided by time. So here P stands for the total storm precipitation, or the total rainfall. R is nothing but the total surface runoff, and I is nothing but the depression and interception losses, and T is the time period of the surface runoff. So basically the value of W index is less than phi index. Why? Because here all the losses are taken into account. Whereas in the case of phi index, all the losses, whatever the losses such as the surface depression storage and the interception losses, are not taken into consideration. Hence, the value of phi index will be obviously greater than the value of the W index. So in case of W index, all the losses are taken into account. So here you can see I suffix A is nothing but depression and interception losses. So now here these are the equations, that is the indices are mathematically expressed as phi index is equal to P minus R divided by the time period. So P is nothing but the total precipitation minus the runoff. So that will give you the infiltration in that particular time period. So whereas W index here, the losses are taken into consideration. So hence the equation is P minus R minus I suffix A during a time period. So where P is the total precipitation, R is surface runoff, and I is the initial losses like the interception losses or the depression storage. So the W index is more accurate than phi index because it subtracts the initial losses. So here, obviously the phi index value will be greater than the W index value, whereas the W index value give a more accurate result when compared to the phi index, because here the minor losses, what are the minor losses like interception losses and the surface depression losses are taken into account. Now you can see here interception loss. Now what do you mean by interception loss? So now whenever a precipitation takes place, some portion of the rainwater, is intercepted by the forest vegetation, and which will take some time, so it takes some time to reach the ground surface because it is intercepted by the forest vegetation. So such losses of precipitation is called as the interception losses. Now, before precipitation reaches the soil, it must pass through whatever the vegetation cover is present. In urban areas, buildings and other structures acts as the intercept or precipitation. So vegetation cover retains some of this precipitation and it will return to the atmosphere by evaporation or sublimation. So this amount of water which will not reach the ground surface and it will be returned back to the atmosphere. It will be returned back to the atmosphere is called as the interception loss. It is intercepted by the forest vegetation. Now, typical interception losses. So the interception losses will be very high in the beginning of the storm, and as the storm proceeds, the interception loss starts depleting and it attains a constant rate. It is almost similar to the Horton's infiltration curve. So typical interception loss curve. So initially the rate of interception will be very high in the beginning of the storm, and it reduces in an exponential form and it attains a constant rate. Now, the intercepted precipitation may follow one of the following three possible routes. Now, whatever the water that has been held by the forest vegetation, some portion will be returned back to the atmosphere without reaching the surface, but the remaining portion held by the plant leaves will reach the ground surface and it will take some time. Now, it may be retained by vegetation as surface storage and returned to the atmosphere by evaporation or the process of sublimation is called as the interception loss. Now, some portion of the water that is held by the plant leaves, so it can drip off plant leaves to join the ground surface or the surface flow. So this is known as throw fall. So the remaining water after the interception loss, it will fall on the ground surface through the plant leaves in the form of drip. So it is called as the throw fall. So next is the rainwater may run along the leaves and branches and down the stem to reach the ground surface. So this part is called as stem flow. Now if you see this figure, P is the precipitation and C is the canopy interception. So this is the forest vegetation. You can see here. So C is the canopy interception. F is the forest floor. So this is the ground surface, forest floors interception. Now you can see T is the throw fall. That is the whatever the water that is held in the plant leaves, it will fall down in the form of drip. So it is called as throw fall. And whatever the water that comes down through the stem or branches of the tree, so it is called as stem flow. So this figure clearly explains how the process of interception losses takes place. And now this is the evaporation. So evaporation is nothing but you can see the water vapor rises to the atmosphere through from the open water surface area like ponds, reservoirs and lakes. Now next we shall discuss the major losses of precipitation. So we have already discussed what is the interception losses, and also what are the infiltration losses and how to estimate the infiltration losses by means of using the equipments like single ring infiltrometer and double ring infiltrometer. And also we can also estimate the amount of infiltration by using the Horton's infiltration equation. Now next let us discuss what is evaporation. So in this process water changes from its liquid to gaseous state. So evaporation is nothing but the water changes from its liquid state to gaseous state. Water is transferred from the surface to the atmosphere through the process of evaporation. So evaporation is directly proportional to the vapor pressure, whatever the vapor pressure. So it is given by E suffix W, and also it depends on the atmospheric temperature, and also it depends on the wind speed and heat storage in the water body. So these are some of the causes which directly influence the rate of evaporation. Now evaporation process. It is the process in which a liquid changes to the gaseous state at the free surface below the boiling point through the transfer of heat energy. So basically it is nothing but the transfer of heat from the surface to the atmosphere. So when some molecules possess sufficient kinetic energy, they may cross over the water surface. The net escape of water molecules from the liquid state to the gaseous state constitute evaporation. So basically evaporation is nothing but the water changing its state from liquid to the gaseous state. So now influencing factor. What are the factors that influence the rate of evaporation? So vapor pressure. The rate of evaporation is proportional to the difference between the saturation vapor pressure at the water temperature EW and actual vapor pressure in the air. So it is nothing but the difference in the vapor pressure at the water surface and also in the atmosphere. So this vapor pressure is given by EL. EL is nothing but the rate of evaporation is given by. So I request all of you to mark your attendance in the chat box. So the time is so I will continue in the next class. So I'll stop the session now. So we shall meet on Monday at 10:45. So till then, have a nice day. Thank you. Goodbye.